Formal charge is something that we use to make sure that the structures we're drawing match with what we have determined about the structures experimentally. When we began drawing Lewis structures, it seemed to all work very, very well, and somewhere along the way, some of the experimental evidence showed things like the length of a double bond where we're predicting a single bond. So we came up with this idea of formal charge to help explain why if you draw a structure one way, it's preferred to the molecule versus if you draw it in a different way. Use the formula for each atom. So for the first sulfur atom, we know that sulfur has 6 valence electrons minus all the lone pairs. He doesn't have any lone pairs showing on him, so that would be 0 minus half of the electrons in the bonds. So there are 2 electrons in that bond, 2 electrons in that bond, 2 electrons in that bond, and 2 electrons in the bond. So half of those 8 is 4. So it's sulfur, it's 6 minus 0 minus 4, which gives you plus 2. Now, if you look up on any YouTube, anywhere, this formula can end up getting simplified. And what you will see is that people will say valence electrons minus dots minus lines. So if we do that same thing for our sulfur, he has 0 dots and he has 4 lines. So you'll see the shortcut. That usually helps people remember it better. For the double bonded oxygen, he has 6 electrons, valence electrons. He has 4 lone pairs, and he has 2 bonds. So that gives him a formal charge of 0. Now, if they're oxygen that is single bonded, there's 2 of them, but they're going to come out the same way. They have valence of 6. They each have 6 dots, and they each have 1 line. That's minus 1. So the way we represent this is if it's 0, we don't mention it. If it's got a charge, we do mention it, and we put a circle around it. So for a single bonded, this one will turn out to be -1. That one turns out to be -1. And our sulfur ends up being +2. So that's how we show that formal charge. This is a compound that's formal charge could be improved. Now let's look at the one on the right. Sulfur, 6 valence electrons minus 2 dots, or 2 electrons in a lone pair, minus 3 bonds. So that's +1. And all of our oxygens are single bonds, and so they are 6 minus 6 lone pair electrons minus 1. So that's -1. So in this case, this shows like this and like this. Notice that when you add up the formal charges, so like this is +1, and then you have your minus, 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 it adds up to the charge of the complex. And like over here, it's +2, it adds up. What's really going on? Well, what we're really saying is this. Our sulfur comes over with this many electrons. So you can tell one of his electrons is in each of the bonds with the oxygen, but he's got 2 extra. So to make him look like that, he loses those 2 electrons to somewhere else. We'll move him in a minute, but he's going to have to lose those 2 electrons. That's why we say that this is +2, because he's going to have to lose them to somewhere else on the molecule. Now let's take this oxygen. Let's match it up right here. This matches. So notice he provides the other electron in the bond, but look, he's got an extra electron. That came from somewhere. I wonder where he came from. Maybe the sulfur. So one of the sulfur's electrons actually ended up going over there to make that spot. Now let's pull another oxygen over. And notice we've got an oxygen electron in that bond. But again, this sulfur, he has to give his electron over here So see, it's not exactly an even situation of what all's going on with electrons. It's like they kind of get a little shuffled about is how this ends up looking. In either case, though, when you look at it like that, you can say, oh, I see how sulfur lost 2 electrons from its atom. That's why he's +2. Oh, I see why these oxygens over here on the side gained an electron each. It was to make them 8. And then you can also say, oh, over here, this oxygen, his formal charge is 0. And yeah, that makes sense for his formal charge to be 0. I'm going to move this one over, because you can see how they all are in the bonds that way. Again, we're not saying exactly that this is exactly what happens. What we're saying is that when we count the atoms up, it can tell us and help us see the stability. Let's see what happens on the other atom. Take this sulfur. You bring him in over here. So he has a match for almost every bond except for one. So you can see he has those bottom lone pairs, and he has a spot everywhere except for one. So that one electron is probably going to have to go somewhere else. Let's go ahead and bring in our oxygen. So there's one. Okay, so we could say that that electron, that was sulfur's, came over here and went there. And that's why our sulfur's formal charge is +1. And then you come over here, and you're like, okay, he fits with this bond, except that he has an extra electron. That extra electron came from somewhere else. See how this is a -2 charge? It's kind of like saying that it was paired up with a calcium that gave up 2 electrons to make that -2. So one of those 2 electrons went there, and you'll see that the other electron kind of matches up. But the other electron went here, because there's actually 2 there. But this isn't what we want to have happen. What we want is for all of the electrons to kind of be hanging out with their atoms. So what can we do to fix this? Let's look at this one on the right first. What if we, and this can only happen with atoms that can do more than 8 electrons in the middle, but sulfur can. Let's see if we can move them down. What if we move them right there and make that a double bond? Would that fix at least the sulfur-oxygen situation for one of them? Yeah. So if we do the formal charge now, that sulfur is 6 minus 2 minus 4, it's 0. If we do the oxygen, and we now have a double bonded oxygen, so that's 6 minus 4 minus 2 is 0. That's a double bonded one. So those 2 are great. We still have a little bit of issue with the single bonds, but because we've fixed our central atom in at least one of the oxygens, we're going to call that good. So, and that's how it turns out happening in nature too. So 6 minus 6 minus 1 gives us -1. So there we go. And that's acceptable. Now what we're going to do is we're going to go ahead and look at this one over here and see if there's something we can do to help this one on this side. Remember again, sulfur can move around and it can be more comfortable, because the reason we can do this is because that sulfur atom can take more than 8 electrons. So we could do that, and we could do that. So what we're suggesting now, you'll notice here when we do this formal charge, so our sulfur is 6 minus 0 minus 6, which is 0. And then our oxygen is 6 minus 4 minus 2 equals 0. So everything in this complex is 0, which is a much better situation than what we had up here. Now go determine the formal charges of the last 3 molecules on your worksheet. Change the bonding if needed.